Hey guys, in this video I'm just going to show you a quick revision of the previous problem plus a little bit more. We already know that the total work over two angles, let's say between pi and 3 pi on 2, is going to be equal to the area under your curve. So this right here will refer to your work done by your bicyclist over these two angles. We also know that the area under this rectangular section is going to be equal to your average work done between these two angles. Now, we also know that the area that's left, which is what I'm drawing in blue, delta E, is going to be equal to your greatest fluctuation in kinetic energy, which is going to be the magnitude of the difference of these two terms. So we can write delta E as being the magnitude of your fluctuation of energy. So this is going to be E max minus E min. E max minus E min. Can we simplify this term anymore? As it turns out, we can. We know because the system's purely under rotation, our maximum kinetic energy will refer to our maximum rotational kinetic energy, which is going to be equal to a half times by I omega 2 squared, where omega 2 is going to be equal to your maximum angular velocity. On a similar note, E min can be written as a half times by I times by omega 1 squared, where omega 1, you've guessed it, is your minimum angular velocity. We can simplify this whole thing out a little bit more, noticing that a half and I are common coefficients, and write it as omega 2 squared minus omega 1 squared. Noticing that this is a difference of two squares, we can rewrite this as a half times by I times by omega 2 minus omega 1 times by omega 2 plus omega 1. This is where we're going to define a few more terms, so bear with me. I'm going to define the coefficient of fluctuation of speed, c, as being omega 2 minus omega 1 divided by your average angular velocity. Right, where your average angular velocity, assuming an equal distribution of angular velocities, is going to be omega 2 plus omega 1 all divided by 2. Now this is where I play the game of substitution, and I'm going to sub them both into here. Once I do that, I'm going to be left with delta E is going to be equal to a half times by I times by this bracket, which can be shown to be C omega average, times by this bracket, which can be shown to be equal to 2 omega average, and presto, I can simplify this entire expression, noticing these terms cancel off, to give I is going to be equal to delta E divided by C omega average squared. I hope that makes sense. Now let's talk a little bit about your moment of inertia. Whilst it's true that your moment of inertia refers to your moment of inertia of your entire system, the moment of inertia of both your pulleys, your shaft, and your bearings are roughly negligible. That's because your pulley is made of light plastic, your diameter of your shaft is very small, and your bearings are also very light. So your moment of inertia, therefore, refers almost exclusively, at least for practical purposes, to your moment of inertia of your flywheel. Consequently, your angular velocities, omega 1 and omega 2, refer to your angular velocities of your flywheel as well, which, because they're connected to this shaft, refers to your angular velocities of your shaft as well. Now let's say for practical purposes, we want to limit the angular velocity of our shaft to 1475 revolutions per minute, and let's say 1525 revolutions per minute. I hope that makes sense.